So let's consider the function f at x is the absolute value of x. Here, x is a real number. The question is compute the derivative, so f prime at x when x is bigger than 0. We also want to compute f prime at x when x is smaller than 0. And then we want to compute f prime at x when x is equal to 0. So if we compute these derivatives, then we see how to apply the formula we simply wrote before. And then we'll be able to see how to evaluate that limit and know whether the function is differentiable at the point of interest. Okay, so we start with the following. Let's start with the first one. Let me call this I triple I. Okay. So, solution. Our goal is to compute, we wish to compute the limit. Let me say as change in x. Okay, let me simplify the notation and say as h tends to 0 of f of x plus h minus f at x divided by h. So here now, our f at x is absolute value of x, and our interest is when x is bigger than 0. So we compute this limit and see what it will give us. I wish to emphasize something, please. Some students make the mistake of carrying limit all through whenever they want to compute the limit. It's wrong. What is right is first evaluate this quotient. When you simplify what is available on the quotient for you, and then get this last expression for the simplification. At that time, you'll be able to know whether when you take the limit as h tends to 0, that limit exists or not. If that limit exists, then you can compute, you can say, oh, this is what the limit is. But if it does not exist, you'll be able to see that that limit does not exist. We have dealt with the concept of limit of functions a lot, that we know how to compute the limit of given function. Realize here that when you evaluate this quotient, you get a function of x, and that function, you get a function of h, and that function of h is what you want to know whether the limit exists as h tends to 0 or not. So please do not continue to write limit of this, you express, you get to the next level, you write limit of that, and so on and so forth. No, it's wrong. Okay, so let's evaluate, like I said, first the quotient f of x plus h minus f of x divided by h. On the numerator, we're going to have this is absolute value of x plus h minus absolute value of x. Then we divide by h. Now, our x is positive. Like I mentioned when I introduced h, here I want h to be a positive number. Okay. So, since h is positive and x is positive, because we're dealing with I component of the problems we posed, so x plus h is a positive number. And by the property of absolute value of real numbers, the absolute value of any positive number is equal to itself. And therefore, this is x plus h. Again, x is positive, so it is equal to its absolute value. Then I divide by h. You agree with me again that from here, this will give us h divided by h. And h over h is 1. So now it is clear to us that if we take limit as h tends to 0 of this quotient, it means taking the limit as h tends to 0 of this constant one. And we saw when we were computing, when we were learning the limit of functions, that the limit of any constant is equal to itself. Constant function is itself. Therefore, when we take this limit, so as h tends to 0, f of x plus h minus f of x divided by h, which is equal to 1, tends also to 1. Hence, f prime at x is exactly 1. If you like, before I write this so that you follow, so f prime at x, which is the limit as h tends to 0, f of x plus h minus f of x divided by h is exactly 1. So this is what we're able to get. So the derivative of this function is 1 when x is bigger than 0. All right.